All right. So what we're going to start looking at is what's alternating series. So we're going to look at series where some of the terms are negative. And so what we looked at for the past couple of days is comparison tests. Those work or those can work when all of the terms in the series are positive, or when for large K, all the terms are positive. So if they're eventually all positive, then you can use the comparison tests. When you start talking about series that have some negative terms, primarily alternating series, then we use a different set of tests. We use some other stuff in order to figure out what's going on. So I want to actually look at first, though, if you talk about a series AK, and then you talk about the series absolute value of AK. And so AK is just some random series where you have a bunch of terms added up, maybe some positive, maybe some negative, maybe all positive, maybe all negative, I don't know. And then the sum where you first take the absolute value of all the terms and then you add those up. And so I want to know, of those two sums, if it's an infinite sum, of those two sums, which one has to be larger if they're not the same? So if they're not the same, which one would have to be bigger? The original series or the sum of the absolute value?
Sum of the absolute value.
Sum of the absolute value, because the only thing that could change, the thing that could change is that the terms could get bigger. Does that make sense? Okay, when would these series be exactly the same? So when would these two be the same thing? If AK what?
Goes to zero.
If it goes to zero, maybe, but more on it. What would mean that if you go from here to here, it does not change? How would that happen?
If it's not alternating?
If it's not alternating, if all the terms here are positive. Does that make sense? Okay, so if all the terms in the original series are positive, then when you take the absolute value, nothing changes, and so you have the same series. All right, the idea that, though, when you go from the original series to the absolute value, the idea is that if it's possible that it stays exactly the same, it's also possible that it gets bigger. So if we think that through, there's more to the proof, but the idea is that if the sum of the absolute value of AK converges, then the sum of AK has to converge. Okay, so if the sum of the absolute value of AK converges, then the sum of AK converges. That theorem is called the absolute convergence theorem. We're not going to go through a proof of that theorem, but one good way to think about it is to think, okay, when you take the absolute value, the only thing you could possibly do is, it's possible you would keep it the same, but if you're changing it, the only thing you could be doing is making it bigger. So if you make it bigger and it still converges, then the smaller version probably should converge as well. And like I said, that's not a proof, and that's part of the proof, but it's not the entire proof. You can go through the book, and I think they prove that in detail, but that's kind of the idea. Does that make sense to everybody?
Okay. Just to be clear, if the absolute value diverges, that doesn't mean the series diverges?
Correct. So this means exactly what's written. So if the absolute value converges, then the original converges. If the absolute value diverges, the original series does not have to diverge. Does that make sense? Okay. All right. So when you talk about two series, when you talk about the sum of AK and you talk about the sum of the absolute value of AK, then we're going to come up with a new term to describe what happens to the original series. So it is possible for both of these to converge. I'm going to write the four combinations of these. So if that converges and that diverges, if this diverges and this converges, and if this diverges and this diverges. So, okay, so if we think about that theorem, and we think about these various combinations, these are all the four combinations of if one of them converges, the other one diverges, or whatever. One of those four lines is not possible based on the theorem that we've got on the top of the screen. So which of those combinations cannot happen based on what that absolute convergence theorem says?
The third one.
The third one is not possible. Okay, this is not possible because if the absolute value converges, then the original must converge. So it is not possible for the absolute value to converge, but the originals to diverge. Does that make sense to everybody? Clear? Okay, so we're going to come up with a little bit different terminology, and you actually saw it on the instructions of the Series 3 handout. When they both converge, so in this top case, then what we say is that the original series converges absolutely. So we say the original series converges absolutely. And what that means is the series itself converges, but so does its absolute value. Does that make sense? Okay, so if a series converges and its absolute value converges, then we say that the series converges absolutely. If the series converges, but when you take the absolute value, it diverges, then the series itself, the original series, converges, but we say that it converges conditionally. That means that when you do have the negative terms in there, it converges, but if you make everything positive, that makes it too big and then it diverges. Does that make sense? And then if AK diverges, its absolute value does too. So we don't make a distinction and we just say, okay, the sum AK diverges. In that case, the sum of the absolute value has to diverge. Does that make sense? Any questions so far? Okay, so I want to talk about, before we get into examples of this stuff, I want to talk about this series. So the series 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5, and so on. I want to know, does that series converge, diverge, or do we not know?
Diverge.
That series diverges, that's right. Somebody explain why that series diverges. How do we know?
Harmonic.
Harmonic.
That's the harmonic series. So we know this series diverges. That's the sum 1 over k from k equals 1 to infinity. That's the harmonic series. We talked about a while ago why that diverges, and we kind of take that as fact now. Okay, if we take this series instead, so if I take the sum k equals 1 to infinity of -1 to the k over k, that's the series -1 plus 1/2 plus -1/3 plus 1/4 plus -1/5 plus 1/6 plus -1/7, and so on. Does that make sense? Okay, so we've not said what that series does, but we call this the alternating harmonic series. And we've proven already that the harmonic series diverges because it goes to infinity. How do we know for sure that the series, the alternating harmonic series, that sum would have to be less than the sum of the harmonic series? Maybe it still goes to infinity, but maybe it goes slower. Why would every partial sum, though, necessarily be smaller than the harmonic series? How do we know that based on that second series?
Because the terms alternate.
The terms alternate, so half the terms are negative, which is going to make it a lot smaller. Does that make sense to everybody? Do we see why? Okay, it turns out that this series converges, and we're not going to go through a real formal proof of that, but we're going to do something called the alternating series test that will prove that that series converges. It turns out it converges because the negative numbers make it small enough where it no longer goes to infinity. It goes to a convergent sum. And so in this case, the series 1 over k diverges. The series -1 to the k over k, the alternating harmonic series, does that converge conditionally, converge absolutely, or does that diverge? What does that series do? How would we describe it?
Converges conditionally.
Yeah, just conditionally. And the reason we know that is because what happened, take the absolute value. So here, if this is AK, then the sum of the absolute value of AK is the sum 1 over k. You're making all the terms positive. You go from this series to this series, that's the absolute value. So this is an example where the series itself converges, but its absolute value diverges, and the series converges conditionally. Does that make sense to everybody? We clear? Any questions so far at all? Okay. All right. So we're going to have two results that we use for alternating series. So yesterday and the day before, we were talking about series with all positive terms. Now we're going to talk about series with a bunch of negative terms. And for the most part, we're going to be talking about alternating series. Does that make sense? Okay. So we're going to use the absolute convergence theorem, and then we're also going to use something called the alternating series test, which we'll write in a minute. But directions for now are going to say show whether or prove whether the series converges conditionally, converges absolutely, or diverges. All right, and so we're going to start by looking at the sum k equals 2 to infinity of -1 to the k over k to the third power. And so when we look at series that are alternating, first of all, what makes this alternating? Meaning it's like the one up here where it's negative, positive forever. What about this indicates that it's an alternating series?
The -1 to the k.
The -1 to the k. So if you look at the homework from last night, there was one with -1 to the k that wasn't alternating, but it was because you added 2 to it. And so -1 to the k plus 2 no longer alternates. But when you have -1 to the k times or divided by a bunch of stuff, that's going to alternate the sign. So -1 to the k is alternately 1, -1, 1, -1, 1, -1, and then divided by a positive number means you switch positive to negative. When that happens, almost always, what you're going to start to do is you're going to start to look at the absolute value instead. And so we're not doing a comparison. We're just going to say, okay, we don't like to deal with an alternating series directly. What we want to do instead is we want to consider this other problem that we like better. So we're going to consider the sum of the absolute value of -1 to the k over k to the third. We're going to figure out what the absolute value does. Whoops, what's that? We're going to figure out what the absolute value does. And so the absolute value of this, absolute value of -1 to the k is 1. The absolute value of k to the third is k to the third. -1 to the k, the absolute value is 1 because it alternates 1 to -1, so it's always 1. The absolute value of k to the third is k to the third because that's always positive. That makes sense? For 2 to infinity. All right, so we figure out what that does. What does the sum 1 over k to the third do?
Converge.
Converges. How do we know that that converges?
The P series test.
It's a P series. Yeah, perfect. So this is a P series where P is 3, which is bigger than 1. Does that make sense? Okay. And so then does the absolute convergence theorem tell us anything about this problem?
Both converge.
They both converge. So if you take the absolute value and it converges, we can go back and say, so the original series, -1 to the k over k to the third, converges to by the absolute convergence theorem. Does it converge conditionally or does it converge absolutely?
Absolutely.
It converges absolutely. So we know it converges absolutely by the absolute convergence theorem. And it's a little weird when you word it this way. Oops, by the absolute convergence theorem. Because the answer is almost the same as the name of the theorem. But it does. The answer itself is converges absolutely. Your rationale is the absolute convergence theorem. That make sense? Any questions? Okay. So then the second question I want to look at is the sum k equals 4 to infinity of -1 to the k over the square root of k. Okay, so in that series, we again, it's alternating. So we start by looking at the absolute value. So we say, okay, consider the sum of the absolute value of -1 to the k over the square root of k. That's the sum of 1 over the square root of k, which is the sum of 1 over k to the 1/2. Does that make sense? That series diverges because it's a p series where p is 1/2, which is less than 1. So we do this part on the right first. Does that make sense? Okay, what does the absolute convergence theorem say in that case? So if it says the sum of the absolute value of AK converges, then AK converges, what does it say when the absolute value diverges?
AK can converge or diverge.
Yeah, so AK, we don't know. It could converge or could diverge. So that theorem says nothing about this case. Okay, when this happens, we're going to come back and finish problem 2 in a minute. But when this happens, we try to use what's called the alternating series test. Okay, the alternating series test is for series like this. It's when you have the sum, k equals whatever to infinity, doesn't have to start at 1, of -1 to the k times bk. Okay, so AK is like the whole original thing. The bk is the non-alternating part. So it's the part without the -1 to the k, or it could be like -1 to the k plus 1, whatever it is that's making it alternate. BK is the non-alternating part. Okay, so if BK is positive, if BK is, I'm sorry, let's do the limit next. Limit of BK is 0. And if BK is decreasing, okay, so BK, the non-alternating part, if that's positive, that guarantees it's actually alternating because you're taking a positive and then a negative and then a positive and negative times a positive number. Okay, so if BK is positive, that means it's actually alternating. If the limit of BK is 0 and if BK is decreasing, then the sum, -1 to the k times BK, converges. Okay. So there are 3 conditions that you test, or 3 conditions that you show. The 3 conditions are about the non-alternating part of the series. If those three conditions are true about the non-alternating part, then the alternating series converges. Does that make sense? Okay, so let's go back up and look at the series -1 to the k over the square root of k. So the first thing we do is we look at the absolute value and prove that that diverges. That's useful because that now proves that the original series, it could converge or could diverge, but if it converges, then it converges conditionally because its absolute value does not converge. So we do need the proof of that part in order to prove that it does not converge absolutely. Does that make sense? Okay, the next thing we do is now we go to the alternating series test. So here, bk is 1 over the square root of k. So it's the non-alternating part of the series. We show that those three conditions are true. So first, bk is positive. So 1 over the square root of k is greater than 0. That's clearly true because square root's always positive. You got a positive divided by a positive, and so the whole thing is positive. The second thing is the limit as k approaches infinity of 1 over the square root of k is 0. And so on this one, that limit's very easy to show. It's 1 over infinity, and so it's 0. And the third thing is bk is decreasing. And so we prove that. We can do that by showing that the derivative of an equivalent like f of x function is negative. We can show it by doing bk plus 1 is less than bk in this case. So that's what I'm going to do is say, okay, bk plus 1 is 1 over the square root of k plus 1. That's clearly smaller than bk because the numerators are the same and the denominator of the first one is bigger. Does that make sense? Okay, and so since those three things are true, then the sum -1 to the k over the square root of k converges conditionally. By the alternating series test. That makes sense? Okay, any questions on that? That's good.
So if it's anything other than converge absolutely, we have to use this or another test.
On most of the problems, like Max, again, like you know how on that homework yesterday, like the first 22 problems were all basically the same.
Yeah.
So on all the standard problems, that's the case. That if it converges absolutely, we're going to do this, like on number 1. If it is one where when you take the absolute value, it diverges. If it's alternating, chances are it's still going to converge, and it's going to converge conditionally by the alternating series test. Let's talk a little more about that in a few minutes when we've gone through a couple more examples. But for standard problems, yes, there are always exceptions if you throw in weird stuff. Does that make sense?
Okay, thanks.
Other questions? Yeah, no problem. Other questions to hear? Okay.